So this is a short introductory video to the gases and climate lecture. So this will cover some of the basic chemistry that you kind of need to know to understand how gases interact with liquids, particularly water. And this is important because it determines what the concentration of these gases are in the ocean, and to a certain extent also to the atmosphere, which makes it relevant to climate because it determines how much of maybe greenhouse gases, how much of them are in the ocean and how much is in the atmosphere. It also determines how much gas that's in the ocean that's important for life can be there as well. So this is an important topic, and these are important things that you'll need to know to understand them. So first of all, there's this concept of what we call Henry's law. Okay, so this is a relationship which kind of helps explain what the concentration is of a gas dissolved in a liquid relative to the overlying atmosphere. Okay, so the atmosphere above, so if we've got kind of a liquid here in a jar, okay, this is an analogy for the ocean and the atmosphere. Okay, now the atmosphere above will contain lots of different gases. Okay, so we refer quite often to the concentration of any one gas in the atmosphere by this term partial pressure. Okay, so that's essentially the pressure of the gas above the liquid if only one of the gases we're interested in was in the atmosphere. So for instance, if it would be the pressure of, if we were interested in the mixing of, say, oxygen in between the atmosphere and dissolved oxygen in the water, the partial pressure of oxygen in the overlying atmosphere wouldn't be 1 atmosphere of pressure, okay, because the atmosphere is not just all oxygen. It would be kind of 22% of 1 atmosphere. Okay, so if we've got looking at, say, carbon dioxide, which is about 400 parts per million, volumetrically wise, so that would mean that we've got 400 millionths of an atmosphere of carbon dioxide pressure overlying the water, and that pressure of carbon dioxide is basically forcing some of these molecules of gas into the liquid. Okay, so it's not liquid CO2 or not liquid oxygen, it's dissolved, so it's kind of aqueous. It's in a similar way that maybe salt might dissolve in water, the molecules of gas are dissolved in the water. Now the concept of Henry's law is that this proportion of partial pressure in the overlying atmosphere to dissolved concentration is at a constant. So if you increase the concentration in the atmosphere, you'll increase the concentration dissolved in the liquid. Okay, so we have this term, the solubility constant. Okay, which describes the relationship between how much of the gas is dissolved in the liquid. Okay, and the partial pressure. For example, we've got at 25 degrees C, and we've got 1 atmosphere of pressure. We can get 1.5 grams per litre of carbon dioxide into the water. Okay, so that's if the atmosphere was 100% carbon dioxide. Obviously, it's a lot less than that. Okay, now you'll see here that this solubility constant is different. Okay, for different gases. Okay, so you can see here that the nitrogen you can get a lot less nitrogen into the water than you could for CO2. Okay, and this is because the nitrogen molecule is a diatomic molecule that's completely non-polar. So it finds it very hard to kind of like jostle in between the water molecules. Whereas CO2 is a slightly polar molecule, okay, so it can interact with the water and dissolve in between the little clusters of water. Okay, so in addition to this increased solubility of CO2 in water, I mean, first of all, making CO2 soluble in water, that's really good for the atmosphere, because that means that we keep our concentration of CO2 in the atmosphere lower, because more of it can dissolve in the ocean, and that's kind of like good for the climate, because if the solubility of CO2 was lower, that means we'd have more CO2 in the atmosphere, more greenhouse gas warming. Okay, and we'll see in a little bit, well, that we can store there's another reason why CO2 is kind of kept in the ocean a little bit more. So in addition to this kind of high solubility of CO2, there's another reason why we can get even more carbon in the ocean, and we'll come on to that in a bit. So this is a picture of some dolphins splashing against some waves, but just to point out that this exchange between the atmosphere and the ocean is kind of largely it's quite a slow process if you just have a very still kind of bit of water overlying underneath some atmosphere. But if you have things like waves, which kind of have lots and lots of tiny little bubbles in, which basically take little packets of the atmosphere and force them into the ocean, creating an enormous surface area and vastly increasing the exchange of gas between the atmosphere and the ocean. So this equilibrium between the concentration of the atmosphere and certainly just the surface ocean, okay, it's very easy to exchange gases between the two because we have this kind of intense mixing at the surface layer. Okay, getting gas into the deeper ocean is another thing, and that's much more difficult. So I mentioned this term solubility constant, and of course it's not actually constant. So it turns out that at different temperatures, okay, you can get different amounts of gas to dissolve in the water relative to the concentration or partial pressure in the atmosphere overlying. Okay, so we've got the solubility of gas per kilogram of water. So this is the amount. If we had 1 atmosphere of pure kind of gas, so pure CO2, we could get much more of it, okay, to dissolve at lower temperatures than we can at high temperatures. Okay, so this is kind of analogous. So at high temperatures, the kinetic energy of the molecules of gas are moving around a lot faster. So when they're in the water, it's a lot easier for them to kind of escape out into the gas phase. So it's therefore much harder to get them kind of back in. Okay, so just to point out here that there's a strong temperature dependence on gas solubility, and this is true for all gases, not just carbon dioxide. It's important because kind of if we look at, globally around the ocean, we can see that there are some places where there's a high flux of CO2 into the ocean, and that's these blue regions up here and down here. And then there's also these red regions where the water is warmer, where there's a flux out of the ocean, okay, into the atmosphere. So where the water is warm, it can hold less CO2, so that tends to force it into the atmosphere. But when the water is cold, we can put CO2 from the atmosphere into the ocean. Okay. But moving on now to this special property of CO2. So when CO2 dissolves in water, it doesn't just dissolve. There are a series of reactions that occur, which go something like this. So we take CO2 that's maybe gaseous, okay, and that dissolves in water to form aqueous CO2. So this is that solubility of CO2 in water by Henry's law. But as soon as it's dissolved in water, it can actually, there's a chemical reaction that happens when CO2 and water react, and they form this chemical species here, which is called carbonic acid. And this species is a very unstable molecule. It doesn't really like to hang around. So as soon as this molecule forms, it either basically back reacts to CO2 and water again, or it can break apart and it can lose a hydrogen ion and become this molecule here. This is bicarbonate ion. So you can see it's negatively charged. Okay, this molecule here also is unstable. Okay, so this can spontaneously break apart and lose another hydrogen ion to form this doubly negatively charged ion called the carbonate ion. Okay, so what happens is that you get some CO2 dissolve in water, and then it forms this guy here, carbonic acid, which then breaks apart into bicarbonate and carbonate ion. Okay, and what this means is that this can basically hide away these carbon species, because these are not gaseous. Okay, so they're not capable of being in the atmosphere. So that means that we can basically lock away these forms of carbon, and these can't interact with the atmosphere. Now, that means that if we equilibrated the atmosphere and the ocean with CO2 aqueous by Henry's law, and then we take away some of the concentration of this guy over here by forming these guys, that lowers this concentration, which means that it puts the balance of the CO2 out of equilibrium, so it draws more CO2 from the atmosphere into the ocean. Okay, until we get to a stage where we have enough of this and this that the exchange between these kind of backwards and forwards reactions starts to balance out, and we then have a concentration of CO2 that's equivalent by Henry's law to what's in the atmosphere. So it turns out that most of the carbon in the ocean is in fact these species here, okay, and only a small amount is this. So this means that most of the carbon in the ocean is locked away from the atmosphere in these ionic forms, okay, which are highly soluble, and only a very small amount, maybe 1% of the total carbon in the ocean, can actually equilibrate with the atmosphere. Okay, so this is another way of writing out these reactions. So these, rather than being one long series of reactions, are actually three separate reactions. So CO2 reacts with water to form carbonic acid. Carbonic acid spontaneously breaks apart into bicarbonate ion and hydrogen ions. And then that bicarbonate spontaneously breaks apart into this carbonate ion and another hydrogen ion. Now these are backwards and forwards. These are equilibrium reactions. So if you leave the system for long enough, you'll reach an equilibrium state where the rate of reactions forward and backwards are equal to each other, and the system kind of calms down. Okay, but the key thing about this is that if you add CO2 to water, if you keep on doing that, you'll form all of these carbonate species, and those reactions will produce hydrogen ions. Okay, and hopefully you should know that if you add hydrogen ions to a solution, you're making it more acidic. Okay, so you're lowering the pH. Okay, so this is the effect of adding CO2 to water, is that you acidify that water. So this is ocean acidification. So a consequence of that is also that because that hydrogen ions are in those equilibrium reactions, okay, if you add hydrogen ions, that forces those reactions back towards having more CO2. So those equilibrium exchange reactions between all of the carbon species are dependent on pH. So if you have more hydrogen ions, that forces you to a lower pH, where you should have more CO2, less bicarbonate, and almost no carbonate. So I should point out that these graphs are on the left and the right. These are the same graph, okay? So they're just showing the trends in slightly different ways. So you've got pH on the bottom, so this is acidic, basic, acidic, okay? So this is lots of hydrogen ions, this is very few hydrogen ions, lots, very few. And so if you've got a very low hydrogen ion concentration, that forces those three reactions to the right-hand side, okay? Because you're taking out the products, sorry, so that basically the reactants kind of want to make more of that kind of stuff now. So that means that at low pH you've got mostly this carbonate ion, and then at progressively higher, acidity or lower pH, you'll have more of the bicarbonate ion and more of the CO2. So this has got CO2 star up here, and that's because the carbonic acid, that H2CO3, is so unstable. We basically group together CO2 and the concentration of that there as one kind of component. Okay, which is because that molecule is so unstable. It's probably it's equal to the concentration of CO2 aqueous. Okay, so the key thing here is that the CO2 dissolves in water, reacts with it to form these dissolved inorganic carbon species, and the relative proportions of those are dependent on the pH. So at the pH of 7 and a bit, which is kind of what the ocean is kind of at, or maybe actually 8 and a bit, 8.1, something like that, we have maybe 9-10% of the carbonate ion. It's kind of here. we have mostly 90% of the bicarbonate ion. That's most of this, and we have a very, very small amount, maybe a tiny amount here, of aqueous carbon dioxide. So this is the only guy that can interact with the atmosphere. Okay, and if we've got a pH of around where the ocean is, then that means that only a small fraction can interact with the atmosphere, and that basically determines actually what the atmospheric concentration is. Okay, so